Hello everyone. Today we're going to talk about work. In physics, work is the energy transferred to or from an object via the application of force along a displacement. Work done by a constant force is equal to force times distance or displacement. Newton's second law of motion says that when an object moves along a straight line with position function as t, the force that's acting on the object in the same direction is given by the mass m times the acceleration a. We know that on Earth, when an object is falling, the gravitational acceleration is g, which is 9.8 meter per second square when we're using international unit. So the gravitational force is equal to mass times g. Example 1. How much work is done in lifting a 1.2 kilogram book off the floor to put it on a desk that is 0.7 meter high? The force to lift this book is equal and opposite to the gravitational force. So we have the force to lift this book is equal to m times the gravitational acceleration and is equal to 1.2 kilogram times 9.8 meter per second square. And that will give us 11.76 Newton. Notice that the unit Newton is equal to 1 kilogram times 1 meter per second square. So the work done in lifting this book off the floor and put it on this desk is equal to the force times the distance, which is 11.76 Newton times 0.7 meter, and that is about 8.2 joules. 1 joule is 1 Newton times 1 meter. Example 2. A 20-pound monkey climbs a tree to a height of 15 feet. Find the work done if the monkey reaches that height in A. 10 seconds, B. 5 seconds. To solve this problem, we're going to use the constant force work formula. Notice that here, the 20 pound is the weight of the monkey. It is a force. So F over here will be equal to 20 pounds. The distance the monkey traveled, the displacement or the distance traveled is 15 feet. So multiplying, we get 300 foot-pounds. Notice that the amount of time that it takes the monkey to climb the tree doesn't change the amount of work done. So the amount of work done will stay the same regardless how much time it takes. So this 300 foot-pounds is an answer to both A and B. So work done by constant force is equal to that constant force times the displacement. Now what about work done by a variable force? Suppose there's a particle moving from A to B, and there is a continuous force F acting on this particle. We're going to use calculus to derive a formula for the work done by a continuous force. Step 1. Set up the x-axis and locate the origin. So over here, we're going to let the x-axis to be this horizontal line. passing A and B. And we're going to locate the origin over here. In calculus, we like to chop things up into small pieces and then add them up. So we chop this interval a to b into n subinterval with equal width delta x. On each subinterval, say the I subinterval, let's pick a sample point xi star. I star is just any arbitrary point in this subinterval. Now, because the force function f is continuous, a small change in x is going to produce a small change in the function value. So when delta x is small, delta f of x will be small. So the force f is almost constant on this subinterval. And so we can use f of xi star to represent the force on that whole subinterval here. Now, because the force is almost constant, so we can use the constant force work formula to approximate the work done on the I subinterval. Let's call that Wi. That's equal to force times distance. So the force here, we use f of xi star to represent the force, and the distance the particle move from x of I minus 1 to xi is delta x. So this is Wi. Step 4. Now we're going to add up the Wi's, and we're going to get this Weimar sum here. Step 5. Letting n go to infinity, the limit of this Weimar sum is the definite integral of this force function where x go from a to b. We now arrive at this formula for the work done by a continuous force. The work done by moving the object from a to b is equal to the integral of this continuous function f, where x here go from a to b. So if we know the force function and we know a and b, we can find the work done by evaluating this integral. Now let's go over one example. A heavy rope 60 feet long weighs 0.3 pounds per feet and hangs over the edge of a building 130 feet high. How much work W is done in pulling the rope to the top of the building? So here is a rope 60 feet long and weighs 0.3 pounds per feet. And this building over here is 130 feet high. We want to find out how much work is done in pulling this whole rope here to the top of the building. So the rope will be completely to the top. I'm going to go over two ways to do this. Let's place the origin at the top of the building, and the x-axis is pointing downward. We'll try to use this formula to calculate the total work done. So we have to first find the force function. Notice that when we pull up the rope, the force is equal to the weight of this part of the rope that is hanging at the edge of the building. The rate of this part of the rope that is hanging over the building is equal to the linear density times the length of this part of the rope. So it's 0.3 pound per feet times x feet. And that is 0.3 x pound. So using the formula for the work done by a continuous force, work done is equal to the integral of this force function, where x over here will go from 0 to 60. So the work done is equal to the integral of this force function, where x go from 0 to 60. Evaluate this integral, we get 0.3 times x squared over 2, where x goes from 0 to 60. Substituting, we get 540. The force over here, the unit is pound, and the displacement here, the unit here is feet. So the unit here will be foot-pound. Solution 2. This time we're going to use we minus sum. Place the origin at the top of the building, and the x-axis is pointing downward. So we divide the rope into n subinterval with equal width delta x. Because the rope is 60 feet long and divide into n subinterval, so delta x is 60 feet divided by n. Now we're going to focus on one particular subinterval, say the I subinterval. And looking at this segment over here, we're going to pick a sample point, which is any point on this subinterval. Let's call that xi star. The work done on this I segment here will be approximately equal to the weight of the segment times the distance that this segment here moves. Now, because delta x is small, we can consider this segment is going to move xi star distance to the top. The weight of this I segment here is equal to the linear density 0.3 pound per feet times the length of the segment, which is delta x feet. So we should get 0.3 times delta x pound here. The distance that this segment moves is about xi star. The product of this will become 0.3 xi star delta x, and the unit here will be foot-pound. Now we're going to sum up all those Wi, the work done on each segment, and let n go to infinity. The limit of this V minus sum is equal to this definite integral of this function, and x here go from 0 to 60, because this row here will go from 0 here and to 60. Evaluate this integral, we also get 540 foot-pound. Part B. How much work is done in pulling half the rope to the top of the building? So in this case, half of the rope will be at the top of the building, and half the rope will be still hanging at the edge of the building. Since the rope is 60 feet long, so 30 feet rope will be on top of the building, and 30 feet rope will be hanging at the edge of the building. We're going to use this formula directly, so we need to find the force function. We'll think of this in two pieces and consider the work done to this upper half of this rope and also the work done for this lower half of the rope. So let's divide this row here into two pieces. Let W1 to be the work done for this upper half of this row, and W2 would be the work done for this lower half of the row. The work done for this upper half of the row, this part of the row will be pulled completely to the top of the building. So it's going to follow a similar thinking as in part A, except this time the length of this row here, this top half of the row here is 30. So the integral here will go from 0 to 30. Evaluate this integral, we get 135 foot-pound. Notice that the bottom half of the row is going to be lifted 30 feet and still hanging here at the edge of the building. The force acting on this part of the row is equal to the weight of this rope, and it is a constant. X over here will go from 30 to 60. The weight of this part of the row is zero point 0.3 times 30 feet. 0.3 pound per feet times 30 feet, which is equal to 9 pounds. And it is a constant force. Evaluate this integral here. We get 9 pounds times 60 minus 30, and we get 270 foot-pounds. Notice that this lower half of the row is shifted 30 feet to the top. The force over here is constant as equal to the weight of this part of the row. So the work done for the lower half of the row, we can use the constant force work formula, and we use 9 pounds, which is the weight of the rope, times the distance moved, which is 30 feet. We also get 270 foot-pounds. Adding the work done for the upper half and the lower half, we get the total work done is 405 foot-pounds.